so for this, we're going to look at a lot of different polynomial characteristics, where the mins, the maxes, all that stuff is located, and how many terms you can have. So it's going to be a lot of little information. Any one question by itself is not going to be too difficult, so that's kind of nice. But you do have to know all the little pieces of information. So there's a lot of information here that talks about the degree, leading term, leading coefficient, and what all these are. So I'm going to talk about those piece by piece as we go through. So let's see. Get that a little bit bigger. There we go. So starting here, right? As for the leading coefficient, so the coefficient of the biggest degree. So of course, find the biggest degree, which would be right here, right? And the leading coefficient would be -5, right? So what would the leading coefficient be on B? Right? Biggest degree right here. Right? So it's not necessarily leading as in the front, but leading as in, the biggest. All right. Now, if it's factored, you can figure out what the biggest term is just by multiplying the first of each one together. So x times x squared times 10x, what does that equal? Right? Or, yeah, we'll say that's, well, it's 10, of course, and x to the 1, 2, 3, 4th power. Right, so leading coefficient here is just 10. Okay, totally doable. The degree is just where we got the leading coefficient. So of course 4. What would we have here? 5, and over here we already multiplied out and got 4. All right, turning points. Turning points. What is a turning point? Well, it's exactly that. You guys know that a parabola, which is x squared, right? How many times does it turn or go from increasing, decreasing, or decreasing, increasing, right? That's going to be just one time, right? It just turns one time. If you have x to the third, right, it could look like this. So it turns twice. It goes up, it goes down. So you'll notice there's a pattern. It's always one less than the degree. So if this is the third degree, it turns twice. If it's a second degree, it turns once, and that's what this n-1 means right here. So if we want the turning points, we just take the answer above, subtract 1 from it. So just subtract 1 from the degree. Okay. Not too bad. Right. Just small little definitions. These are going to be quick little problems on quizzes because we have to know where these things are. And if we know the leading degree, we know the general shape of the graph, right? So an x to the 4th, just because it's an x to the 4th, I know, and it's opening is with a negative x to the 4th, it's going to have some sort of shape like this, like an M shape, right? And that's why it's important to know what the leading coefficient is and what the degree is, because I can already know that both sides are going to go to like negative infinity on the left and right hand side. Same thing here with a 5th. It's going to be look something like this. It's going to go up and down, and it's going to look like that. Right? I know the left side is going to go all down forever, negative infinity. The right side is going to go positive infinity. And there's going to be different things happening in the middle, but just by knowing that alone and knowing it's positive, I know that to be the case. So that's the whole reason for knowing all this stuff. All right, so let's talk about all these different little ups and downs, right? We call them mins and maxes. Mins and maxes. And just identifying where they are. Right? So we have a lot of definitions here, which you don't really need to know all this language here, where it says f of b is greater than f of x. Basically, we're saying, right, if this is the case, it's called a relative. Relative just means in that local area. So sometimes referred to as a local min or local max. So what would be a local maximum? Well, right over here in this general area, that's the highest point. That's local max, and so is this one. Local max here, local max there. And then we also have the local minimums, or relative, right? So it interchanges what they call them, whether relative or local. course, this would be the min right there. Now, there are places that are lower than this or smaller than this, right? These go to negative infinity. You never count negative infinity or positive infinity as mins and maxes. So even though there are places that have smaller y's on this graph, they're not counted as a local min because you can't really be at infinity. Infinity is a concept that means it's gone on forever in a certain location or a certain direction, but does not have a location. So with these, we need an actual number as an answer, where infinity is not a number. All right, so far so good. And we like to know, well, where are these located? So we usually say, well, at x equals -2, x equals +2 are the local maxes, and the local mins located at x equals 0. Often it's just the x value. Sometimes they want the coordinate, but usually it's just the x value. Okay, so flip it over. It's going to just ask a few more questions about all this, just to make a little bit more sense. And it does say to use some colors here. If you don't have it, it's all right. Just do different shades or something like that. So it says on the graph on the right, shade the intervals of increasing in green. So that's what I'm going to do. Grab my green. Increasing, of course, from left to right. So we're going up. I got to take that off. Yeah, so from here to here, increasing. And then from here to here, increasing. And decreasing in red. There we go. And this, it says state those intervals. What are they? So where is it increasing? Two different places. I'm just going to write the word increasing with a colon. And then this, since it goes down with an arrow, that's considered negative infinity. This will be considered positive infinity because it goes left forever and right forever. So the first increasing would be negative infinity with a parenthesis, comma, and it goes right until you get to -1. And that we can use a bracket. And then also from 2 to infinity. Parenthesis. All right, and increasing, let's do that in red, decreasing. Would just be from -1 to 2. All right, label local extrema. That's the plural of mins and maxes. So you want to say all the mins and maxes, that's just called extrema, or the extremes. All right, so of course this would be our max, and this would be our min. So notice how the colors change at the mins and maxes. So that's what they're getting at right here. What's the connection between the relative extrema and the increase and decreasing? Well, it goes from increasing to decreasing, decreasing to increasing at those points, right? So let's see here. A max is where it goes from increasing to decreasing. So if we were trying to figure out, well, where's this graph changing? And instead of finding all the intervals and looking at the entire graph, if I could just find out what the max is, well, that's when it goes from increasing to decreasing. And for the minimums, it's the opposite, right? When you're going down here, a minimum is where it changes from decreasing to increasing. To increasing. So, and it might be stated obvious, but it's going to be helpful for us to have this kind of written down ahead of time. Okay. What is the least possible degree? Right? How do you know? Okay, so how many turning points are there? Right, turns once here, one turning point, and again right here. second turning point. So what degree would that be? It's the reverse of what we just did earlier. So therefore, it must be 1 greater than that. So that must be an x to the third power. So earlier we started with, right here, the degree and subtracted 1 to get the turning point. So if I'm going to go this direction, if I have a number of turning points from looking at the graph, I have to add 1, and that gives me the degree. So it's just asking the same question, but in reverse. Okay, just a x to the third, or you could say third degree. Like that, out of the way. All right, good to go. Let's go on down. It says, on each graph, circle the local extrema and draw a dot at each 0. Circle the local extrema. So you can do these on your own, just see if you get the same thing. Watch the first few if you want. And remember, 0 means y equals 0. Where does the y's equals 0? Where the graph intersect with the x-axis is the same question. So x-intercept, a 0, where y equals 0, all the same thing. So that's right here, dot, dot, and dot. Okay, so do that for the rest. See how many you can do on your own. Just check with mine as you are doing them. And it says, what is the connection between the location of a 0 and the extrema, the mins and maxes? Where do you notice the mins and maxes are in relation to all the zeros? And so if you look at each one of these, the blue circles are always between 2 red dots, right? All the blue circles are always between 2 red dots. So the mins and the maxes of the extrema are always located between 2 zeros. Between 2 zeros or 2 x-intercepts, however you want to say it. Let's say zeros. Now, a min and max can also be at 0. So you look at the first one, like this max is not located between 2 zeros because it is 0. So like right here and right here, those are the exceptions when the min or max is actually a 0 as well. So you can put that in there as well and say extrema can also be an x-intercept if you like. But this is useful because if we're trying to find where these are, like where are these mins and maxes? Well, you guys already spent a bunch of time in Algebra 1 and Algebra 2 finding x-intercepts. So if we know where the x-intercepts are, well, we can find the mins and maxes. Nothing more than that. All right, so we got, that's local or what's it called, relative maxes, right? So there's also another concept called absolute, where it's the most highest of the entire or most lowest of the entire graph, right? So usually this occurs with the, what's it called? With even functions, something to the second power, fourth power. There's going to be an actual very, very high point. Like nothing goes above this. Like there's nothing going to infinity as well. So in this case, this becomes not just a max, but an absolute maximum. Right there at -1. Oh, no, not -1, positive. Okay. So it's located at 1 comma, what is this? 1, 2, 3. Located at 1 comma 3. Another way of saying that is f of 1 equals 3. It's the same concept. And this does have an absolute min because you'll notice there's no arrow on this. So if this had an arrow, we couldn't use -infinity or infinity as an actual answer. But because this graph actually does stop right here, this is the lowest point on the entire graph because it has a dot. So we can say this is a min. So at -3 comma, what is this, 5? At -3 comma 5, or at f of 3, -3 equals 5, same thing. You do have an absolute min. So either it's a graph that doesn't go up to, the very highest at some point, not including infinity, or very lowest at some point, not including -infinity, or it has these dots on the end where the graph actually stops right there. Those could be absolute as well. It is definitely -5. That's what I wrote. Thank you. Good catch. All right. All right. Now let's put these two concepts together. Okay. So remember, the relative is just where it goes from changing from increasing to decreasing, right? Any increasing to decreasing, or increasing or decreasing to increasing is a relative min or max. All right, and we're going to report usually just the x values. So we can go through this and do these things one by one. So let's see here. Let me try the one on the left, and then you guys can try the one on the right. Let's see here. So local min, right? Local min. So this is a min. It's the minimum of this area, right? Because it does include endpoints as well. I left that off here because it does say, or it's an endpoint. If that had an arrow and went to infinity, we'd not be including that. So -3.5. That's one. And what's the other one? Here, min 1.1. And local max -1.8. And 3. Now, of these, which one are the absolute highest and absolute lowest? All right, so which one for sure? The lowest minimum is because there's no graph below this line, right? So this is the lowest it goes right here. So -3.5 is the absolute. Well, up here, the graph does not go higher than this right here, right? Stops right there, so 3 is the absolute max. So a point, oh, not 3. Yeah, 3. A point cannot be can be a relative and a absolute. And if it wanted the minimum, it could also report the actual coordinate as well, if it asks for it. By default, just do the x's. Right? But if it asks for the actual location, then we'll put the whole thing, 3, 8. All right, so try B, see how that goes. See if that's works for you. And I'll be doing it up here as well. If you want to watch. the lowest places on this graph are going to be when it goes to negative infinity, but we are not allowed to use that as a number, so we just say none. So we'll say it does not have a global, but it does go to negative infinity forever. All right, not too bad. Try C and D. See if you can do some of that on your own this time. Goes up forever, goes down forever, so none. Okay. Now remember, if either of these endpoints, either of these were endpoints, meaning they had dots on them, like let's say this was a dot, this would be the global max, and this would be the global min if it just had a dot at the end. But with arrows, again, they go into infinity, negative infinity. We can't use that as an answer. So when you get over here, that definitely matters. So keep that in mind. Okay. So min, 2, 2.5. And max, we have negative 3, negative 7.5, and 4. So of all of these relative, which one's the smallest? That'd be at 2.5. And of all the local maxes, which one's the largest? That would be 4. All right. Not too bad. It's a lot of little definitions today. Okay, next part, a little bit about even degree and odd degree polynomials. This has to do with how many turning points there are and just kind of what I mentioned earlier, what the graphs look like. So in general, this is a fourth degree polynomial. You want to think of this as a W shape. And so anything fourth degree just has this W shape. Both the left and right hand side go to positive infinity. If this was a negative x to the fourth, it'd be flipped upside down and look like an M. So in general, this is x to the fourth, and then negative x to the fourth would look just, would look like this. Okay. Now, where these terms and stuff are will vary drastically depending on what the other terms are. Okay, and but most of the time it just looks like this. It could look something like this, like an x to the fourth could look like this, and just it still goes up in both directions forever. Just the zeros could be like really close to each other, and you might not be able to see as many turns, but once you zoom in, you can find them. With a x to the third, right, x to the third, it looks something like this. So all x to the thirds have this type of shape. Right? And if it's inverted, negative x to the third, just flip it. So it's really about the end behavior, that the left goes down forever, the right goes up forever. And if you flip it, the opposite is true. And you notice here, I just kind of went right through here. This one, I put the turns on there. All right. And down here, we got negative x squared. So we know that x squared, that is a parabola. So negative x squared will just look like a parabola opening down. So notice how the even, the x to the second, and the negative x to the fourth, notice how both sides go down on both of them. So that's why we can categorize them as an even degree and odd degree. So all even degrees have the same behavior. Right? Both sides are going to go up, or both sides are going to go down with even degrees. With odd degrees, both sides are, one side's going to go up, one side's going to go down always. And this is true for a straight line as well, because you guys know a straight line, which is an odd degree to the first degree, one side goes down forever, one side goes up. So that's the first degree. Or if it's a third degree, you have 1 and 1. And that's the big picture we're kind of trying to look at for all of these. And I don't think we're going to actually look at these actual, but if you want to go back and do that with Decimus, you can. Okay, but it's more important just to know the general pattern here. So if you go back to all these questions, they keep on asking you, what's the connection between zeros and extrema, right? What's the, how do you know the pattern, right? So everything you're trying to, gather here also has to do with finding patterns and using that later on. All right, so let's just skip down to the last part here. So what we want to do is, given a table, just be able to sketch and roughly find out where all the mins and maxes are without having to really use a calculator or Desmos or anything. So what you can do is you can do like a crude little graph here on the side. And see what you come up with, right? So 0, negative 40. 2, 0, 4, 8, and 6, 0, and 8, 16. So just based upon that alone, I can tell that this has to go up, come back down, and then go back up. So it definitely has to be a cubic function or something to the third degree. X to the third of some kind. Now, of course, it could be, and we know it's going to be positive x to the third because it starts low and finishes high. But it has a bunch of stuff after it that we can't figure out yet. But we can figure out, it says the polynomial has a local minimum at one of the points on the table. So you can see here on the graph, the local min is right here. At 6. And how do you know? But by looking at the table only. So remember, a minimum is where it goes from decreasing to increasing. So we could find out this information even if we didn't plot this, just by looking at the table, seeing that it does that. From 8 to 0 it decreases, and it's a 0, so I know it's going to go back up, and then it goes back up and hits 16, so decreasing to increasing. And you can write that out in many different ways. Like we know has a local min at x equals 6 because on the table it goes from decreasing to increasing, something of that nature. Okay, and I'm going to let you write that out the way you want to write it out. And then same language for how do you know where the local max is, right? Max. So right here, right, it goes from increasing to decreasing. Increasing to decreasing. So we know this must be a max, right? This must be a min. So I'll leave that, just leave that alone as is, right? And you write out everything I just said, just, you know, in full sentences. But on this one, always you could just graph it a little bit, and you can see that as well. But hopefully at some point we can just get that just by looking at this table and not having to do, you know, any type of estimating or graphing of any kind. All right. Give you a second to do that, and then we'll be done.